This module is designed to serve as a high-level introduction or review of basic RF technology. It is extremely important for anyone involved in Wi-Fi network design or integration to understand the technology and concepts described in this module. Only by understanding this information will an individual be able to effectively design and deploy an enterprise-class Wi-Fi network. RF propagation transmission. I have no intention of doing a deep dive on the properties of RF. However, we need to go over some basics of how RF propagates. Basically, the next couple of slides will discuss the positives and the negatives of what happens to the RF energy between the transmitting device and the receiving antenna. Bottom line is always start with high-quality radios. These, used with an appropriate antenna design and then measuring the RF attenuation, will determine the actual connection range and the data rates that you can expect. RF propagation, range, coverage, and capacity. An important concept is to understand the relationship between range, coverage, and capacity. At first thought, the idea of the more range the better is appealing. However, that is often not the case. The greater the range of a radio, especially when using omnidirectional antennas, the greater the coverage of that single device. This works very well if only coverage is required. However, if performance is also required, then range can actually be detrimental to the network performance. The issue then becomes capacity and how many devices can a single AP or radio effectively support. Just because a radio antenna pair can cover a large area, it must also be able to balance that by what is the appropriate number of users it can usefully support. In educational environments, this may be only 20 users, while at large events, 50 users on a single radio might be deemed acceptable based on applications and user expectations. Networks will vary. More on this topic will be discussed in the following module. RF inhibitors. Once the signal leaves a transmitting antenna, anything it comes in contact with tends to degrade the signal. This includes the open air as well as the human body. There are three main components to propagation loss, and in many ways they are actually interrelated. They're multipath, obstructions, and attenuation. Multipath occurs because when a transmitted signal leaves an antenna, it doesn't just take a single direct path to the receiving client. No matter how directional the antenna, there's always going to be multiple copies of the signal that will be created. When the signal hits an object, whether it's a door, a wall, or pretty much anything, additional copies will be created. This creates a problem as the multiple copies of the same signal will have varying delays and arrive at the receiving station slightly varied in time. These multiple copies serve to distort the received signal, rendering it weaker. This results in reduced throughput, or even in some cases, making the received signal completely useless. This is why you may have weaker signals in some areas of a room and strong signals only a short distance away. Attenuation reduces the signal strength as it moves through obstructions. Be aware that even air is considered an obstruction, so even with no physical obstructions between two antennas, the signal will be attenuated. All objects have different levels of attenuation. The chart on the right shows common accepted values, and however, be aware that there are no guarantees as all construction is going to be different. The only way to provide 100% guarantee of signal coverage and strength for an area is to perform an active site survey. However, in many cases, only a predictive survey is required to provide coverage analysis. RF enhancers. The previous slide may have given you pause about wireless. However, there are also things you can do to enhance the signal strength. One of the most common is antenna design. Antenna design is based on something called an isotropic transmitter. Big name, but really just means a device that transmits equal amount of energy in all directions. This type of device really doesn't exist. However, it serves as a reference for antenna design. When you start shaping the coverage pattern with directional antennas, you tend to reduce coverage in some areas and increase coverage in other areas, in other sectors. The more you reduce the overall coverage, the more you're able to increase the gain in a smaller sector. The traditional dipole, or more commonly called the omnidirectional antennas, which are used by most APs, even cell phones or car radios, etc., slightly reduce the overall coverage, but is able to extend the horizontal coverage. Think of it this way. Think if you had a balloon, and if you're pushing on the top and the bottom of the balloon, you get a little bit less coverage up and down, but the balloon is extended outward horizontally. Same principles apply in antenna design. Basically, the more you directionally focus the antenna, the greater the signal strength and resulting distance in one direction, as you can see in the third graphic. While all vendors use directional antennas for some purposes, Xeris is the only one currently to take the advantage of these principles to gain range and also allow for greater capacity and density. Most AP vendors integrate one or two radios and omnidirectional antennas in their APs. As a result, all clients within the footprint connect to one of these two radios. On the other hand, Xeris uses 2, 4, 8, 12, or 16 radios and directional antennas. Because each antenna has its own directionally focused sector, we're able to get at least twice the distance and 4 times the coverage of traditional omnidirectional antennas. An easy analogy is to consider traditional AP coverage like a light bulb, where the Wi-Fi array has coverage more like a collection of flashlights arrayed in a 360-degree overlapping pattern. Another interesting note is that antenna design works in both ways. That means if a directional antenna will double the transmitted energy going out, it will also double the received energy coming back. An easy analogy here is a megaphone. You could use it to focus your voice so you can be heard further away. Then you can also use it up to your ear to hear better too. Antenna physics works very much the same way. Range dynamics. Don't worry, we're not getting into a math class here. However, there are some basics that everyone needs to understand about RF energy. The most common is RF energy is expressed in dBm or decibels per milliwatt. And by the way, Wi-Fi is a very, very low power technology, typically far less than half that of your cell phone. The signal strength at any point in your network is indicated by an RSSI value. RSSI stands for Received Signal Strength Indicator, basically the energy level at the receiving antenna. Wi-Fi connections can be made with signals as weak as -90 RSSI, but Xeris recommends designing your network so all areas will have a signal strength or RSSI value of approximately -65 or stronger. This is especially important if support of handheld devices like tablets or smartphones are to be supported. As the bottom bullet indicates, your signal strength is a product of the transmit power multiplied by the antenna gain minus the signal attenuation between the devices. This is known as path loss. The received signal is then boosted by the gain of the receiving antenna, and the signal is transmitted to the receiver. The final received signal strength will then define the actual data rates you could expect. SNR. As mentioned on the last slide, the strength of the received signal determines your actual data rate. However, it's not just the signal strength, it's also how much stronger that signal is over the surrounding RF noise. The SNR reading, also called the signal-to-noise ratio, indicates how much stronger the data signal is to the surrounding RF noise. In a very clean RF environment, the noise level will be around -95. In a very noisy area, like a trade show floor with thousands of devices operating at different times and different technologies, the noise floor can actually be in the -70s. By the way, a lower negative number, the stronger the signal is. So for example, a signal of -60 is far stronger than a signal of -70. Back to SNR. At the worst case, if the noise level is stronger than the signal, no communication will occur. The stronger the signal is above the noise level, the higher the data rate that can actually be obtained. The chart on the right shows the SNR values required for the different data rates. A data rate of 6 megabits per second only requires a signal strength a little stronger than that of the noise. However, if you want higher data rates, 54, 65, 300 megabits per second or more, you need the signal to be far stronger than the noise level. This is important because in noisy environments, you will have users complaining that they have a very strong signal, but their throughput is extremely low. The first thing they do is blame the Wi-Fi equipment. However, the issue is probably the surrounding RF noise. This is another good reason to avoid the 2.4 band as much as possible, as it's far noisier than the 5 gigahertz band because the devices that operate in 2.4 are not limited to just Wi-Fi. There's a lot of other devices like Bluetooth, microwave, etc. 802.11 timeline. It's important to review a little about the evolution of Wi-Fi. Today there are 4 primary standards that have been introduced over the last 15 years. We have 802.11a, 11b, 11g, and 11n. There are also many other amendments to the 11n standards addressing issues such as quality of service, security, and other components required to create a reliable Wi-Fi network. So a quick review. Today, all Wi-Fi technologies are designed to operate in unlicensed wireless bands. The two spectrums used are around the 2.4 gigahertz band. This is called the ISM, or Industrial, Scientific, and Medical band. There's also the 5 gigahertz band, also called the UNII, or Unlicensed National Information Infrastructure band. Specific differences between the two bands will be discussed in following slides. One quick note. All information in this presentation as it relates to usable frequencies and available channels is applicable to North America. Other areas and countries have different standards, and in some cases there are additional or reduced RF channels available. So now back to the standards. The 802.11 standard was ratified in 1997, and although it attracted lots of attention, it only offered low speeds of 1 or 2 megabits per second. So to be a viable networking technology, higher speeds were required, and work groups soon got started. The two primary ones, the first to come along, were 802.11a and 802.11b, and both were ratified in around 1999. When these products became generally available, about 95% of the market share went with 11B, as the advantages of greater distance and lower cost of the 11B products operating the 2.4 band outweighed the bandwidth advantages of 11A. Remember, at this point, wired Ethernet was king and wireless was really just being deployed as a hotspot technology, so the greater bandwidth was not as much an advantage as you would think it is. Although the consumers bought into the cost advantage of 11B, 2.4 gigahertz product manufacturers quickly realized wireless would not succeed as a true networking technology without higher data rates. So a new working group was developed to increase the bandwidth available. This was 802.11g group and ratified the newer technology in 2003. The most recent and most talked about standard is 11N and offers speeds from 65 to 300 megabits per second to 450 megabits per second, and even the standard actually allows us to go as high as 600 megabits per second in the future. 11N does operate in both the 2.4 and 5 gigahertz spectrum, so it's considered an upgrade to both 11G and 11A. However, it's most effective when deployed in 11A networks, and we'll see why shortly. Whether 11N ever gets to 600 megabits per second data rates is now debatable, as you can see, there are newer technologies, including 11AC, that offer even higher data rates. You also have 11AD with multi-gigabit data rates. However, that technology is slated to operate in the 60 gigahertz range, and while useful, it will not be a traditional upgrade to today's Wi-Fi networks. 802.11 ABGN overview. There is still significant misunderstanding concerning the existing 802.11 Wi-Fi standards, so let's look a little bit deeper. As I mentioned, the four primary standards are 11A, B, G, and N. B was designed to operate in the 2.4 gigahertz band, where most commercial technologies were being designed to operate at that time. This made the products less expensive, as there was a large collection of component manufacturers making radios in this range. The 11B standard provided data rates of up to 11 megabits per second. The second standard introduced in 1999 was 802.11a. This operated in the 5 gigahertz band, and since fewer manufacturers were making radios in this band, the components were far more expensive. 11a was designed to support speeds up to 54 megabits per second. 802.11g was the next improvement, ratified in 2003, and it added 54 megabit per second capacity to the 2.4 gigahertz band. The advantage of 11G is it's backwards compatible with 11B, so existing clients could be retained at that point. However, there's a serious drawback to creating networks with a mixture of low-speed and high-speed clients, and that is you take a significant network performance hit when you mix the two because, once again, it's a shared environment. Xeris strongly recommends removing all 11B clients from Wi-Fi networks if at all possible. The most recent and talked about standard is 11N, and its design offers speeds up to 150 to even 600 megabits per second. The common speeds today are either 300 or 450 megabits per second. Another advantage of 11N is that technology operates in both bands, so as I said before, it's considered an upgrade for both 11G and 11A. However, as mentioned, and we'll see in the following slides, 11N technology is most effective when deployed in the 5 gigahertz space. Channel breakdown. In the last slide, I introduced the difference between the 2.4 and the 5 gigahertz technologies. The next few slides will get us a little bit deeper. The first thing to realize is the 2.4 band only has 3 available channels that can be used simultaneously without interfering with each other. On the other hand, the 5 gigahertz bands offers up to 24 separate channels. Looking at the top graphic, you can see there are actually 11 channels defined for use in North America in the 2.4 band. What is important to note is that these channels were designed long before Wi-Fi, and they support other technologies such as Bluetooth. These wireless channels are only 5 megahertz wide, and as you can see in the second graphic, a Wi-Fi channel is actually 20 megahertz wide. So in fact, one Wi-Fi channel will consume the space of 4 traditional channels. Lack of this understanding creates a problem with interference if the Wi-Fi network is not designed correctly, such as putting neighboring radios or APs on channels 4, 5, and 6. There are only a few areas where all Wi-Fi vendors are in agreement, but one of them is the need to avoid channel interference. As a result, most recommend only use channels 1, 6, and 11 in the 2.4 band. As you can see, this creates enough separation between channels and essentially eliminates the potential for interference. The 5 gigahertz band, on the other hand, does not have this problem. It has up to 24 available channels that already have the required separation defined. Bottom line here is that using 2.4 technologies limits you to only 3 channels in one area. 5 gigahertz offers up to 24. So for dense deployments, this is a no-brainer. So make sure you understand and appreciate this principle. The additional channels are also extremely important when deploying 11N. One of 11N's advantages is the ability to combine channels to get the higher data rates of 300 megabits per second and higher. With 2.4, you only have 3 channels you can combine. With 5 gigahertz, obviously you've got up to 24 channels you can combine. A lot more capacity in that way. Bands, channels, and total capacity. Based on the bandwidth and the number of channels available in the different technologies, you can clearly see the advantages of 5 gigahertz. 2.4, as I mentioned, only offers 3 channels, providing limited capacity, and it's also prone to interference. 5 gig, on the other hand, offers up to 24 channels, more capacity, less potential for interference. So if you're looking for performance, you need to be focused on leveraging the 5 gigahertz band as much as possible. The 2.4 band is also important to support legacy devices. However, not for delivering high performance. Both bands will be required, though, for some time, and you must design for them. Interference. Here we can actually see the problems associated with the 2.4 band. Note, there is nothing inherently bad about the 2.4 spectrum. It'll always be a useful spectrum. The issues are the limited number of channels and the number of non-Wi-Fi technology devices that also operate in the same band. In the first graphic, you'll see 3 channels, 1, 6, and 11. We then turn on a cordless phone, and as you can see with the green spike, it basically destroys the availability of channel 1, and in this case, you'll lose 33% of your available bandwidth. Even if the same thing were to happen in the 5 gigahertz space, you would only lose 1 channel out of 24, and obviously you have a lot more capacity, a lot other channels that users can roam to. The bottom graphic shows the RF spectrum is viewed from a spectrum analyzer built into every Xeris array. It was taken at a recent interop, and as you can see, the 2.4 band is just maxed out, while there's still plenty of available bandwidth in the 5 gigahertz band. Understanding radio capacity. Okay, we discussed some basic RF information. Now we also need to examine how much usable bandwidth a Wi-Fi radio can actually provide. Just like all wireless clients don't deliver the max amount of bandwidth expected, neither does actually the Wi-Fi technology itself. If you were testing the usable bandwidth of a wired 100 megabit link, it would result in just about 100 megabits worth of available bandwidth to the user. However, that's because with wired you have a fixed, dedicated link. Things are different with wireless. It's a half duplex technology. It's a shared resource technology. You need to contend for access. Most communication between the client and the radio must be acknowledged. RF noise impacts performance, and the data rates will vary even between packets. So obviously there's lots of things that affect your actual throughput. And as I said, as a result of all this, the usable throughput in a production network is significantly lower than what the devices say they are transmitting at. This is the same for all Wi-Fi devices. For a 150 megabit per second radio operating the 2.4 gigahertz band, you can actually expect about 50 megabits of usable capacity. For a 300 megabit 5 gigahertz radio, you can expect about 100 megabits of usable capacity. Note that every vendor can provide higher values in controlled testing environments. However, go to any real wireless network in actual use, and you'll discover results very similar to this. Okay, now once you have an idea of how much bandwidth is actually available, you can now do some basic math to determine how many users a single radio can effectively support. Note I say effectively support. Xeris and other vendors can put hundreds of users on a single radio if we want. However, the user experience will probably be very poor if all tried to simultaneously use the network. To that end, Gartner took a stab at determining what amount of bandwidth should be available to each user in a shared wireless environment and came up with the value of 6 megabits per user on average. So as a rule of thumb, they recommend determine the total number of users, multiply by 6 megabits per second, and that will determine the total wireless bandwidth required. You can then take this number and divide by available radio bandwidth and determine the number of radio's access media devices required to support your network. As you can see, the capabilities of the 2.4 and 5 gigahertz radios vary, so take this into consideration. Once again, this is just a rule of thumb for a starting point. Additional on-site testing is required to determine the actual number of devices and their locations in your own network. This concludes the RF Basics. Thanks very much for listening. If you have any questions, please contact Xeris and we'll be happy to assist you further.